All right, so this video will have two sample problems dealing with the differential form of conservation of mass, or the result of conservation of mass, which is the continuity equation. Um, so again, we're thinking here. We're starting to think about point-wise flows here, and the conservation laws applied to fluid elements, where we're shrinking down our control volumes down to a single point, but kind of still thinking about them in a cubic shape, right? So the elements themselves have cubic shapes, and that gets us to the result that we're the equations that we'll use here. So. But we do, in this problem, we'll still see some control volume in a macroscopic scale showing up here. So the tools we've learned in the past are still going to be used going forward. Okay, so this is 619 in your book, and here's the picture I have drawn here. But what's given you in the problem statement is actually looks a lot different. It just says in a 2D incompressible flow field where U is given as 2x. So that's all that's given, really. Do some things with it, and I'll. One of the main things we're going to do is take the line between the origin and this A, which is at 1, 1, and determine the flow across that surface, where the surface we're really thinking is per unit width into the page. Right? So it's really the flux through that line, but it will make a surface as we come out and into the page. Okay. So now, this is the picture I have drawn. So what I've done here is drawn out the flow field. We know that, and just the U components of the velocity field, that's just given here. It's not that this is our complete vector field, this is just the U components. So we'll just put U only. We don't know about anything about the vertical velocity yet. And as you can see, along the y-axis, we have no flow in the x direction, but as you get further away, so basically there's a diverging flow field away from the y-axis in both directions. And we're just going to focus here on the first quadrant, because that's where we have that line between 0 and 1, 1 that we want to know the flow between. But before we get there, part A is to determine the vertical component of velocity. If we're given that the velocity, we need to be given some kind of boundary condition. So the velocity is 0 at y equals 0. So along the x-axis, we now have 0 vertical velocity. And you'll see we need this boundary condition because this result, we're going to have a differential equation that we'll need to basically solve for an integration constant. So we need some sort of boundary condition to give us how things, or to kind of set that integration constant. Alright, so our differential form of the continuity equation is written here. It's really the full divergence of velocity must be equal to 0 for an incompressible flow, and we see we're given in the problem statement that it's incompressible, so we know this must equal 0, the divergence of velocity. Plug in our u into the du dx part, that just becomes a constant factor 2. So therefore we know that dv dy must be negative 2, and we just integrate this, right? Multiply this by differential length dy on both sides and integrate. The left side just becomes dv. Integrating over dv is just v. Integrating over minus 2 dy is just minus 2y, plus some integration constant, where we integrated a partial derivative with respect to y. And so our integration constant can still be a function of x, or a function of everything that we didn't integrate over, and in this case this is just a 2D flow field, so it can only be a function of x. Now here comes our boundary condition. We're given that at y equals 0, v velocity, our y velocity is 0. So therefore, plug that in, we expect to get 0 when we plug in 0, therefore f of x must be equal to 0. Okay? And so our final form of the vertical velocity is just minus 2y. So at this point we can now draw an entire picture, our full picture, which looks like this. In the light blue here is our vertical component, our horizontal components of velocity. In red are our vertical components, and then the combination, purple, is the full magnitude of velocity with the proper orientation drawn. So our full vector, velocity vector field is, it's always the u component I hat plus the v component j hat. And that's how we've drawn this here. So let's interpret this a little bit. You see I have these two little weird shapes, one square and one rectangle. How did we get there? Well, we know if we're just looking in this positive quadrant, and all the others are going to look pretty similar, but different orientations. But if we're just in the positive x, positive y quadrant, or the first quadrant, we know that as if we put a little fluid element up here, in 3 dimensions we think about them as cubes, but in 2D they're just going to be squares. We start an element up here. Well, it's going to be hit by a horizontal velocity that increases as it goes this way. And so since it's increasing in its velocity, we know that it will be expanding in this x direction. While at the same time, it's also going to be hit by a vertical velocity downward. All of our red arrows are downward. That slows down as we get closer to the x-axis. So therefore, it's going to be compressing in the y direction as we get closer to the x-axis. So as the fluid particle moves from this place to this place, it's expanding along x and contracting in the y direction in equal proportion to assure we have an incompressible flow. All right, so the total volume, the total area in this case, of this fluid element can't change. Okay, so now we're going to take these velocity vectors and answer that second part, which was determine the magnitude of the average velocity of fluid crossing this OA surface, where the OA surface goes from the origin up to this point 1, 1. A is at 1, 1. And just be careful with units. So throughout this process, we might be it's going to be hard to be careful with our units completely, but every time we see an x or y, just note that they're in units of feet, and our UV are in units of feet per second. Again, I've just reproduced the purple velocity vectors from the previous plot, and you know, at points of interest here, right? So again, you see that as we move this way, our horizontal component of velocity goes from 0 and increases outward in the positive x direction, where our vertical velocity starts at some high velocity here and gets lower and lower. So the vertical component of our velocity vectors gets smaller and smaller, but they're headed in that negative direction toward the x-axis. So we have 2 different methods to find this vertical, the average velocity magnitude crossing the OA surface. And every time we see average velocity magnitude, right, what would you get if you multiplied the average velocity of the flow through an area multiplied by its area? That's going to give you the volumetric flow rate. Right? So it's kind of the definition of average velocity, that the average velocity is just the volumetric flow rate over the area. Okay, it's one way to think about that. We could, so I have 2 methods here. You can already see method 1. Method 1, we kind of rely back on our control volume analysis. Method 2, we just rely directly on what the volumetric, or what the average velocity definition is, and what is a volumetric flow rate. So what we really want to do is take the volumetric flow rate through the OA plane here, and then divide by its area. Well, it might look easy, but since the line heads off in this x equals y direction, right? There's a line here that isn't along the vertical or the horizontal. That gets a little bit tricky. So let's look at what I think is the more straightforward way of calculating it, but you have to think about how you're solving it before you get into it. So the first method is to treat this OAB triangle as a control volume. Again, this is kind of like our hydrostatic force, where now it's going to be easy to look at the fluxes through this surface, easy to look at the fluxes through this surface, because those are oriented along horizontal and vertical planes. And then through that, we'll know what the flux is through the OA surface, because for an incompressible flow, our flows in must equal our flows out. So the sum of the flows in must equal the sum of the flows out. Okay, so that's what this is. This is a control volume. We have all our unit normal vectors. The outflow is just the flow through this OA surface. That's what we're looking for in this problem. And the only inflow is the AB surface. Right? We see we have flow coming in here, flow going out there. And what about the OB, the origin to B surface? Well, if we look, there's velocity there, but it's completely vertical, and it's a vertical wall. So our unit normal heads off in the x direction, and our velocity vector is only in the y direction. So v dot n is going to be 0. Okay, so if v dot n is 0, there's no volumetric flow through that surface. Okay, it's just flow along the surface, but no flow through the surface. So all we have to do then is calculate the volumetric flow between A and B, and we know that whatever comes in through A and B must leave through O and A, because this is a steady, incompressible system. Okay, well, we know that the volumetric flow between A and B is just going to be, well, if this is a constant, if the the vertical velocity, right, we need to just take the component that is projected into the unit normal. The unit normal is now completely vertical, so all we have to consider is the vertical component. If that vertical component stays constant, which we know it does, all we have to do is evaluate the vertical component of velocity there and get that constant value and multiply it by that constant area that it flows through. And that's going to be our volumetric flow rate. So this is a special case. This is not a general way of solving this. This is only because our vertical component of velocity is constant between A and B, right? So we're evaluating v at y equals 1. V was just minus 2y, so if we plug in y equals 1 foot, we just get a velocity of minus 2 feet per second. Note that the minus here, it's an inflow. So it's an inflow, so I put a minus because we expect to get a component, or the v dot n we expect to be negative as well. And that's what we see here. The velocity is in the negative direction, n is in the positive direction, but I put in the negative there to account for this being an inflow, so that we get a negative negative. Volumetric flow rate, you can keep signs on that and let the math tell you, or just use your intuition and know what we're talking about. But what I want to get here is positive only volumetric flows. And so because this is an inflow, I put a negative there. And then we get another negative to cancel that one because v dot n is negative. Okay. Our area is 1 foot squared. Well, we know the distance between A and B is 1 foot, and then we'll just use unit width out of the page for another 1 foot. So then we get 2 feet cubed per second. So here's the general way to do this, okay? If we're being more careful. Right, so here's just because I knew something about the flow field. Generally, how we have to solve this, the volumetric flow between A and B is given as the integral of the velocity projected into the unit normal direction, or the unit normal vector, and then that integral over the area of fluxing, right? So our n hat, our unit normal vector, is just j hat, just the unit normal vector in the y direction. And then our velocity is given as, here's our u component in the I direction, and our v component of velocity in that j hat direction. And now we need to evaluate this at y equals 1 to determine our velocity. Therefore, if we do that, this is where we our vertical component just becomes minus 2. We're evaluating this at the AB line, and that's just y equals 1. And so our vertical component there is going to always be negative 2. Therefore, our v dot n is, we just need, right, so this is a projection into our unit normal direction. Our unit normal is just in the y direction, therefore we're only going to pick up our y velocity and evaluate it at y equals 1, we just get a minus 2. So that's minus 2 feet cubed per second. Again, the negative sign is standing in there for this being an inflow. And as I said before, our area there is just 1 foot squared if we're using unit width into the page. So generally, you want to think about the full definition of our volumetric flow rate at this point. Now to get our average velocity, now we found the volumetric flow through AB. And from continuity, we know that must equal the volumetric flow rate between OA, because there's no flow in or out in the OB plane. So our average velocity is just then the volumetric flow over the area. Now we have to be careful here. Our volumetric flow is 2 feet cubed per second. We now found that 2 times from the general way and then the specific way due to the specifics of this flow. But our area for the OA plane is not just 1 foot squared. It's 1 foot unit width into the page, but this distance here well, we have a triangle that's 1 foot by 1 foot, so this length is square root of 2. 1 squared plus 1 squared is 2, and then we take the square root from Pythagorean theorem, right? Okay, so the OA length is root 2, the unit width in the page is 1. We have 2 over root 2, which is just root 2 feet per second, or 1.414 feet per second is our average velocity. Okay, so that's the method 1 to solve for the average velocity through this plane, where we treated this as a control volume, looked at all the inflows and outflows on that control volume, and got our, went a backwards route to get to the answer here. However, we can do this a different method where we just directly calculate what the volumetric flow is between O and A. And this, you have to be a little bit careful, but I tried to fit it in all in one page here. Maybe a mistake. But the volumetric flow rate, again, the definition is the same as we had above, but now we're directly doing it for the OA surface, so the OA plane. But again, it's just the velocity projected into the n hat direction integrated over the area of interest. Where, now in this case, our n direction, we look here, now we're just directly calculating the flow rate through here. Our n hat is going to be in the, positive in the x, but negative in the y in equal proportion, okay? So our unit normal vector is going to be 1 minus 1, but then the magnitude of the 1 minus 1 vector needs to get hit by a 1 over root 2 to make this unit normal, right? To make this its magnitude unit, okay? Another way to, and so I've mixed notations here, but I kind of like it, having all the different notations of writing a vector here. So in the beginning, we talked about u and v as separate quantities, combine them as a vector like we've done here. Another way to write it is with this parentheses notation, where here's our x component, here's our y component. All right, so anyways, another, to write this using our unit normal coordinate vectors, this is just I hat minus j hat divided by that root 2 to make it unit normal, to make it a unit vector, I mean. Our velocity field is, in general, the velocity field for the whole flow is 2x I hat minus 2y j hat. And now we're evaluating this. Our OA surface is the line where y equals x. So we can then replace y with x, and then we just get that this is now 2x I hat minus j hat. Okay, so we're getting to a point where we're writing everything's in terms of x's, I guess. Okay, the most tricky part about doing this directly, though, is that the OA surface, or the OA line, where we're, unit width into the page and out of the page, but the line OA is not along the x coordinate or the y coordinate. So we can define a new coordinate, which is, I'm going to say r here. It's not the r we use in like cylindrical coordinates, but instead it's defined by this y equals x line. Okay, so r is just going to be, in general, we are thinking about it in terms of the radial direction. R in general is just the square root of x squared plus y squared. That just gives us the radius at any place. But now we're limiting ourselves to y equals x. So now if we say y equals x, well then we just get 2x squared underneath and take the square root. The x comes out, but the square root of 2 stays there. Okay, so at least in this first quadrant, we can just use the r coordinate as root 2 times x. So therefore, our dA, as we trudge along the OA line, is just going to be 1 foot into the page times dr, which is going to, now we'll just put in that dr is going to be root 2 times dx. Okay, so our dA, the only reason of doing this is to say as we can integrate in x, right? But it's just going to be that every time we take a unit or an infinitesimal distance in x, our actual area has a size of root 2 as we go along this line. Okay. All right. So back to our volumetric flow rate definition. Now we have everything. We talked about v, velocity vector on the OA surface. We talked about the unit normal for the OA surface, and now we talked about the differential areas for the OA surface. If we plug everything in, the 2x I hat minus j comes from, well, so v, 2x I hat minus j comes from the velocity. Our I hat minus j over root 2 comes from our unit normal, and then the root 2 dx comes from the area. And here's where the units get a little tricky. I I put in the foot here, but note that from our v dot n, we are also going to need, well, we still have an x, which will give us a foot. So we still are missing a 1/2. But we just need to be a little bit careful with the units, but we expect to get the result here is in terms of feet cubed per second. This dot product, right, I dotted with I gives us 1, and then the minus 1j times minus 1j gives us another 1. This is just going to be 1 plus 1 is 2. So this dot product gives us 2. So let's see here. We have root 2 divided by root 2 is going to cancel, and now 2 times another factor of 2 is going to be 4. So we can pull out the 4 feet per second, and then all we have left is we're integrating from 0 to 1 x dx. Do that integral, it's x squared over 2 from 0 to 1. That's just going to give us a 1/2. Therefore, we get this 2 feet cubed per second. And that's the same volumetric flow rate that we found here for AB, which we know needs to be the OA volumetric flow rate. And so you can trudge through the problem as we did before, where just find the average velocity by dividing by the area right here. Okay, so this is a little bit more direct, but a little bit, you have to be more careful with the math. All right, so I have another sample problem, and there's not a problem number here because this is one I wrote myself. This is going to be dealing with stream functions and velocity potentials. I think stream function, this is the proper time to do an example problem on this. And the velocity potential, I'm just going to do it now, even though I'm not sure if this is going to be introduced till later. But regardless, it'll be coming up soon. So if you haven't heard this yet, it'll be soon. So given the flow field, again, we're given the u, we're given both components of velocity now in terms of their dependence on the x and y coordinates. So again, we just have a 2D flow, and this would maybe what's given to you. It's always good to kind of expand them out because we know we're going to be integrating and taking derivatives quite a bit when we're doing fluid kinematics. So part A is this incompressible? From conservation of mass, can we do something with this? And you see part B is going to be, is it irrotational? And again, the point of this is that if we can determine a flow is incompressible, and or we can determine if a flow is irrotational, then we can apply some really simplified versions of our complicated full governing equations to this system, and it makes our analysis a bit easier. All right, so incompressible, we take the divergence of velocity, which is du dx plus dv dy in 2D. Du dx is just going to be, look at the expanded version. Well, the y squared drops out. We just get a -1 and a -2x. And then dv dy, look at the expanded version. We get a 2x plus 1. Okay, well, all the terms cancel each other, right? So it's not that both du dx and dv dy are 0, but they are in equal, they're equivalent, I guess, but in negative. They're equal and opposite. So du dx is equal and opposite to dv dy, meaning that any contraction we get in the x direction as a fluid particle, as a fluid element flows along, we get an expansion in the y direction to counteract that, such that the volume for our fluid element stays the same, and we get a conservation of, we get a conservation of volume in this case, but that's equivalent to a conservation of mass when density remains constant. Therefore, we say it's an incompressible flow. Irrotational, now we're doing cross derivatives, so we have dv dx minus du dy. This is related to the vorticity in the flow. Some people would say this is the definition of vorticity in the 2D flow. So if we look at this, take the v velocity and take the derivative of it in x, we just get 2y. And go up to our u velocity, take the derivative with respect to y, we just get another 2y. So both of those are 2y, and for vorticity, we just have a negative sign in there. So yes, 2y minus 2y is 0. Therefore, this is an irrotational flow as well. So now we can, with incompressible and irrotational flows, we would now be able to talk about a potential flow, which is where a velocity potential shows up. But before we get there, part C is going to be finding a stream function. We can only do this if the answer to A is yes. If it's incompressible, we'll be able to find a stream function. If this is no, If this is not 0, you won't be able to find a stream function for this flow. Alright, so the way we define a stream function is we have two different equations. First is that u is related to the stream function through a y derivative. So our d psi dy, this is psi, d psi dy is now given by our u component. We're going to separate and integrate such that on the left-hand side, we just got the integral of d psi, so we just get the stream function itself, is now equal to the integral of our u component of velocity times this dy. Alright, so do this integral, that becomes y cubed over 3, and then all these terms don't have a y, so they're just as they are, but now multiplied by y. And then we add on an integration constant. Well, again, this is a function that is a function of x and y. It's a 2D field, and we integrate it only in y. So the integration constant can still be a function of x, right? But it can't be a function of y. And what we mean by that is if we go back and take its derivative, this drops out, right? And so even if it's a function only of x, it'll drop out. Okay. Now we do the same thing for the v component, except now we define our v component of velocity, we're really defining our stream function to be d psi dx with a negative as now v. And the reason we have this is basically this definition ensures that this is true, that our divergence of velocity equals 0. Right? By this definition of how psi is defined, this is automatically true. Okay. So with this definition, we do the same thing. Over here we have our v component of velocity, separate and integrate, making sure we have that negative sign in there. Again, we get our stream function defined, so let's see, 2x, we're integrating an x, that becomes x squared over 2, but multiplied by that 2 factor, so we just get minus x squared y, and then this just becomes minus xy. Plus, again, for the same reason, but different here, we have now an integration constant that is actually a function of y. Okay, it can't be a function of x, and we have different functions. And what we have to do now these are really the same psi stream functions, the same 2D fields for the stream function. We need to make sure these are compatible, choosing f of x and g of y in such a way that these are exactly the same, but also making them as simple as possible. So this can be done if and only if it's incompressible. So if it's incompressible, this can be done. You can choose fx and gy to make these completely compatible. If it's not, if it's a compressible flow, you can't find this to be true. Okay? So if we make an observation here, look at these two functions. This is y cubed over 3. Do we see that term down here? No, we don't see it, but luckily that's just a function of y, so that can go into g of y. xy, well, that's a function of both x and y. We better see it down here, and we do. Minus x squared y, that's a function of both x and y. We better see that down here. We do. And we don't have any extra terms in this form either, right? So as long as we make gy equal this part, and then f of x can be 0, and then they're both compatible. Okay, so if we let gy equal this y cubed over 3 and fx equals 0, we both of these hold true. Both of these are valid. And we've made it as simple as possible. So our stream function is just then y cubed over 3 minus xy minus x squared y, where we've combined it and pulled out an xy and made this 1 plus x. Okay, so now we do something very similar for velocity potential. Just like the stream function we can only find a stream function if and only if it's incompressible. So the answer to part A is yes. We can find a velocity potential if and only if our flow is irrotational. If and only if answer to part B is 0. Okay. So if we have 0 vorticity everywhere in our flow field, that's the only way we can find a velocity potential. So our velocity potential, though, is defined in a very similar way to satisfy that that our vorticity is 0. Okay, but in order to remember our vorticity had cross derivatives, so now we're going to see the same derivative showing up here in the velocity potential. So the velocity potential is phi now, and now the u component of velocity is just d phi dx. Do the same thing where we separate and integrate. This is just our u component of velocity. Our velocity potential is therefore xy squared minus x squared over 2 minus x cubed over 3. That's just the integral in x for the u velocity. Now again, we integrated in x. This is really a 2D field, so there's a function of y now over here. Same thing now, d phi dy is defined to be v. We're defining the velocity potential such that that is true. So d phi dy is now given by our vertical component of velocity. We integrate the vertical component in the y direction, and we get these terms. What's left over here is a function of x. We now need to make these two equations compatible by choosing f of y and g of x appropriately. That is only possible if and only if, I guess this can be done if and only if this is an irrotational flow. We already determined it's an irrotational flow, so we must be able to do this. If we determined it was a rotational flow, this would be a lost cause. You wouldn't be able to do this. So we look at these. Xy squared, that's a function of x and y. That shows up in both. X squared, these two terms don't show up down here, but luckily they're functions of x only. So we can just throw them into g of x. And now if we look down here, this term here only shows up down here. We don't see it up here, but luckily it's only a function of y. We can throw that into f of y. And then both forms of phi here are consistent. Okay, so we're letting f of y be this y squared over 2, and this g of x be these two terms. And then here's our velocity potential. Okay, at this point we now have a stream function and a velocity potential. We could go and plot this with some plotting software. That's what I would recommend, and I've done that, but I didn't print it out here. Instead, I just kind of sketched out the results. And this is what the flow looks like. There's a lot going on here. One obvious thing to do is consider particular streamlines. So what the stream function represents is if you set the stream function equal to constants, that should define streamlines, right? So you have an infinite number of streamlines, but try out a few. Plug in psi equals 0. It's an easy one to do. So here is our definition of stream function. If we set this equal to 0, well, we see that there's y's in both these terms, so we could pull out a y. So we have y multiplied by this bit, okay, equals 0. So we have two different kind of roots here for the psi equals 0 streamline, two different paths that the streamlines actually take. One is that y is 0. So along the x-axis, that's our psi equals 0 streamline. And then this term being 0 is another way to get 0 total, right? These are products. So basically just finding roots. But what's left over here are complete lines in the 2D plane, in the xy plane. So what this says is that y squared must equal 3x1 plus x, or take the square root, right? So this is another form of our psi equals 0 streamline. So y equals 0, and then this thing that looks like a square root. Y equals the square root of an x squared term in here. Okay, so that looks like this. Our psi equals 0 streamline, that first one goes along the x-axis, and then the other one has this form, that y equals the square root of something. Okay? Again, this would be hard to plot without using a plotting software, but I did that and just reproduced it here. So all of this is along the same streamline. Well, to have a kink like this in a streamline, right? Streamlines mean that you come to a point, and that's just the path line for a flow and a steady flow here. And this is a steady flow, right? U and V don't depend on time. So what happens at these 2 points? Well, with crossing of lines here can only mean one thing, that at that intersection we have a stagnation point. Well, we can look at that. Where do we get stagnation points for this flow? Well, it's when U and V are both 0. Well, V is 0. Remember now, V was defined to be as, let's see. Right, we're looking for points where both U and V are 0. V is going to be 0 when y equals 0. Okay, that's one There's two different ways. Actually, let's go to this form. This will be easier. When can v equal 0? Well, either y equals 0 or x equals minus 1/2. Right? Those are the two ways that we can get v equals to 0. Okay? So v equals 0 in these two cases, and let's take each of the two cases and then look where u is also 0 there. So at the y equals 0 place, where is u also 0? Well, u is defined here. When does it equal 0? Right? So we're evaluating u at y equals 0. That first term drops out. When is this term also 0? Well, this is 0 when x is also 0. So the point 0, 0 should be a stagnation point. That's when v and u are both 0. Or the second term. Well, this second term is 0 when x is minus 1. So we should get another stagnation point at minus 1, 0. So two stagnation points associated with that condition for v equals 0. The other condition for the v equals 0 is that x is minus 1/2. We plug that into the definition of u, right? X equals minus 1/2. Well, that minus 1/2 becomes a positive 1/2, and then we have 1 minus 1/2 inside here, which is just going to give us another half. So this now says that we're looking for where u equals 0, right? Well, we have y squared plus 1/4. That's never going to be 0, right? Even when y equals 0, that's going to be 1/4. And as y gets away from 0, this just gets bigger and bigger. So there's no solution here. So we only expect to see two stagnation points. And we do that when we plot it. We see two stagnation points at 0, 0 and at minus 1, 0, which are both on the psi equals 0 streamline. Okay? And by looking at the flow directions, by actually looking at the u and v components, you can determine that at the 0, 0 stagnation point, flow is coming in on the A arm of the psi equals 0 streamline and exits on the B arm of the psi equals 0 streamline, where I'm referring to up here. This is the A arm, this is the B arm. And then at this stagnation point, the opposite happens. This flows in on the B arm and flows out on the A arm. So that looks like this. We have two stagnation points. Here's our A arm of the psi equals 0 streamline, and here are our B arms. And we know at the 0, 0, we're flowing in on A, flowing out on B. And at the other stagnation point over here, we're seeing flowing in on the B arm and flowing out on the A arm. So it allows us, by looking at the U and V components, we can then determine the direction of the flow along these streamlines. We can also then, with plotting software, put other streamlines as well, right? And that's what we have drawn here in this light blue. So the dark blue is our psi equals 0 streamline, and our light blue is our psi equals other constant value streamlines. Okay? Let's see. We also have drawn on here in the orange dashed lines are our velocity potentials. And the way this works, again, if you plot this with plotting software, it looks something like this. But the way it works is that these velocity potential equals constant lines must be perpendicular to our streamlines. Right? So these are our equal potential lines, and these are our streamlines. And they just work like this. And so the combination of these two things, when you have both an incompressible and an irrotational flow, is a nice mesh that where some of the lines show you the flow direction, where the other lines then show you the lines that are perpendicular to the flow direction. Okay, so it makes up a nice grid to think about the flow. It's kind of a nice visualization technique. Okay, so the last part of this problem is going to be to determine some volumetric flow rates. So we'll come back to the picture here at the end, and as we go along here. But another thing we can do with the differential form of the continuity equation is, and then once we've defined stream function, we can determine the volumetric flow rate per unit width between particular points or between two streamlines, essentially. So if we're looking for the volumetric flow rate between minus 1, 0 and 0, 0, well, first of all, we know these are our two stagnation points. So, you know, this flow might represent something, a flow you might have. You're modeling a flow using this flow field, and you might want to know so this kind of looks like a sink and a source. So something's coming in and then spewing it out here, and then over here things are flowing in here and then coming out in this direction. And there's an interesting path you can take. Come right along almost this point, and then you'd flow along here and then head out that way, right? So it kind of goes like this and here. So we might be modeling something. I'm not sure what. I don't have an example here, but so you might be interested, what's the flow between our 2 points of stagnation here? And well, we know they're stagnation points, so they are on the same streamline, right? And if you plug them into the stream function, where's my stream function? If you plug them into the what the stream function is, right? We're just plugging in -1 and 0, and then 0, 0. Well, we see 0, 0 is just going to be psi equals 0, and then -1, 0, right? Both of these have the y value of 0, and so these are both going to have a psi value of 0. All right, so these are on the same streamline, is what that means. And then this volumetric flow rate per unit width is just the difference, between 2 points is just the difference in their streamline values, or their stream function values, which is just 0 since they're on the same streamline. Okay, so there's no flow between these 2 points. And if we look at our diagram, between 1 and 2, we're looking for flow across the line that connects them. And velocity there is completely normal to the surface, not tangent to the surface. Right? So again, this is a case where the v dot n we're looking for to be non-zero, and it's completely 0 in this case. There's no velocity component in the normal direction between these 2 points. But if we now look for flow between the origin and now 0, 1, so now we're going up in y. If we plug this into our stream function, this we get 0, and this you get 1/3. So then the volumetric flow rate per unit width, the per unit width is because we're only living in 2D here, and we're talking about per unit width into the page. But the volumetric flow rate per unit width is just the difference in the streamlines, which is now 1/3. Okay? So, and then if you did the same thing, we'll just kind of breeze through the rest of this. If you did the same thing between the origin and going down 1, right? If you plug this in, you get psi 2 is now -1/3. And then the volumetric flow rate per unit width is now -1/3. So what that means is that between these 2 points, right, we have some, and I've kind of drawn it angled here because we know based on the streamline patterns that the flow is generally in this direction. But the line between these two is completely vertical, so really the flow we're picking up is the velocity component normal to the vertical plane here, so it'd be just horizontal velocity essentially. But it doesn't really matter. We're just picking up a volumetric flow rate, and from the origin down 1, we're getting an equal magnitude, 1/3 volumetric flow rate per unit width. So here, this represents volumetric flow between these 2 points. Well, why is one positive and one's negative, and then we just kind of drew them the same? Well, really, the sign that you get for our volumetric flow rate per unit width isn't as important. What is important is just to say that the way this works is that the flow direction is given such that if you're riding along with the flow, the greater psi value is to your left. Okay, so we found that here's our psi equals 0 streamline. Up here is our psi equals 1/3 streamline, and we know that because that streamline crossed through the 0, 1 line, and we calculated that stream function value to be 1/3. So we know the volumetric flow rate through this plane here is 1/3, but what's the direction? Well, it flows such that the 1/3, which is bigger than 0, is on the left side. If we go down to the bottom, for the same reason, we know that this is the psi equals -1/3 streamline because we calculated, we plugged in 0, -1 and found this stream function value here to be -1/3, and then every line that connects it, along its streamline also has that same psi value. And then the flow rate between it is 1/3, but we know that the psi equals 0 must be to the left of the flow because psi equals 1/3 is less in its value. Okay, so that's a pretty complicated application there, but we're starting to see how our differential analysis can be pretty powerful and how we can make nice visualization techniques with our stream function and velocity potential, so we get streamlines and equal potential lines. And then we can actually talk about something with the volumetric flow rates from what we get for the values we get for the stream function. All right, that's it.